We're all familiar with binary, right? The world of ones and zeros. But what if I told you that the standard way we count using binary has well, a hidden flaw, a tiny little glitch that can actually cause some pretty massive failures in our machines? So today, we're going to dive into a really elegant solution designed to stop that chaos in its tracks. Now, I know that sounds a bit dramatic, but it's a very real problem in digital electronics. Imagine a mechanical sensor or any digital system that's just counting. If it gets a number wrong, even for a split second, the consequences can be huge. So the real question is, how do you stop a machine from essentially lying to itself? All right, so here's the plan. First, we'll look at what this binary glitch actually is. Then, we'll check out the single-step solution. We'll see where it's used in the real world, put it in context with other codes, and wrap up with why it's not a one-size-fits-all kind of deal.
Okay, let's jump right in. The binary glitch. So what is this hidden danger? Well, it all boils down to a really small but absolutely crucial detail in how we represent numbers using those on and off switches. Bits.
So, you know how standard binary works, right? Every number has its own unique pattern of ones and zeros. Simple enough. But, and this is the key part, going from one number to the very next can get surprisingly messy. Sometimes it's easy, just one bit flips, but at other critical moments, a whole bunch of them have to change all at once, and that is where things get risky.
Okay, let's look at a perfect example. The jump from the number 3 to the number 4. In binary, that's going from 0, 1, 1 to 1, 0, 0. Now look closely. Every single bit has to flip. And here's the thing about the real world. Nothing is perfectly simultaneous. Those bits don't all change at the exact same nanosecond. So what if that first bit flips just a fraction of a second early? For a tiny, tiny moment, the system might read 1, 1, 1, which is the number 7. And that's the glitch. It's a temporary error for sure, but it can be a really dangerous one.
So, what's the fix? How do we get around this? Well, we need a way to count where we can absolutely guarantee that only one thing changes at a time. And that, my friends, is precisely what gray code was invented for.
And the idea behind it is it's beautifully simple. Gray code is just a special type of binary system where any two numbers next to each other in the sequence differ by only one bit. That's it. That's the whole trick. No more multiple bits flipping at once, which means no more risk of those glitches. It's just a fundamentally more stable way to count.
And this table right here really shows you the magic. Just look at that bits changed column for the gray code. It's always 1, 1, 1, 1 all the way down. Now think back to our problem child, that jump from 3 to 4. In standard binary, it was a messy 3-bit flip. But look at gray code. Going from its version of 3, 0, 1, 0 to 4, 1, 1, 0 is just one single clean flip. Problem solved. The glitch is just gone.
Okay, so how do you actually create these gray code numbers? You might think it's complicated, but the process is actually super simple. It all starts with what we call the most significant bit, or MSB. That's just the fanciest way of saying the bit all the way on the left. The rules are really easy, so let's just walk through an example to see how it's done. All right, let's take this binary number, 101011. First step is the easiest. That first 1 on the left, it just drops straight down. That's our first gray code bit. Now we go back to the binary number and add the first and second bits together. 1 plus 0 is 1. So that's our next bit. Then we do the next pair. 0 plus 1 is 1. Then 1 plus 0 is 1. Then 0 plus 1 is 1. And now for the last pair. 1 plus 1. That's 2, which is 1, 0 in binary. The rule says we just ignore any carries, so we only take the 0. And voila, our gray code is 111110. See? Simple and totally effective.
So yeah, this is way more than just a clever math puzzle. It has some absolutely critical uses in the real world, anywhere that preventing these kinds of errors is non-negotiable.
Okay, so for example, picture a robotic arm. It's moving, and a sensor has to read its exact angle and turn that physical position into a digital number. If that sensor used standard binary, it could glitch and momentarily think the arm is in a completely wrong position. But if it uses gray code, as the arm moves smoothly, the digital output also moves smoothly, one single bit at a time. No chance for a glitchy reading. It's also super important for things like error correction and just making digital circuits simpler to design.
And that single-step change? It's the secret sauce behind a tool called a Carnot map, which is something engineers use all the time to simplify complex circuits. The whole map is laid out using gray code. Because of that, any two squares right next to each other only differ by one single thing. And why is that a big deal? Well, it makes it incredibly easy for an engineer to visually spot patterns and group them together. By doing that, they can take a really long, complicated logical equation and shrink it down into something much smaller and more efficient. And that saves time, it saves money, and it means less complex hardware.
So it's important to remember that gray code isn't the only code out there. It's really just one tool in a huge toolbox of different binary codes, and each one is designed to do a very specific job. So let's kind of zoom out and see where it fits into the bigger picture.
You can classify these codes in a bunch of different ways, and gray code, as you can see, is what we call a non-weighted code. And this is a really key difference. See, in standard binary, you know how each column has a value? You've got the ones place, the twos place, the fours place, etc. That's what we call a weighted code. But in gray code, the columns don't have a fixed value. You can't just look at a 1 in a certain position and know what it's worth. It's all relative. Just to give you a couple of other examples, here's BCD on the left. That's a weighted code. And on the right, you've got XS3, which is another non-weighted one, kind of like gray code but with its own unique properties. Again, it's all about picking the right tool for the right job.
Okay, so this begs the question, if gray code is so fantastic at stopping errors, why don't we just use it for everything? Well, it turns out its greatest strength is also its biggest weakness.
And here is the trade-off, plain and simple. That whole non-weighted thing that makes it so stable and reliable for counting, it also makes it absolutely terrible for doing arithmetic. You just can't take two gray code numbers, add them up, and expect to get a useful answer. It just doesn't work that way. So for any kind of calculation, we have to stick with our good old friend, standard binary. When you think about it, gray code is just a perfect example of one of these elegant, almost hidden solutions to a really fundamental problem. It's a great reminder that just beneath the surface of our digital world, there are countless clever systems just like this one, working quietly in the background to make sure everything runs the way it's supposed to. It really makes you wonder, right? What other invisible codes are out there, silently keeping the chaos at bay, one bit at a time?